Armature converts electrical power to mechanical power in the form of torque and transfers it via the shaft. Shaft is movement part and it's connected to armature. Field magnet consists of two poles, north and south pole. Field magnets are concave and cylindrical shape and therefore produce radial magnetic field. Direction of the magnetic field is from north to south pole. Slip rings S1 and S2 are connected to the armature and rotate together with it. The slip ring consists of a circular conducting material that is connected to the armature rotor windings. Slip rings are used to bridge, transfer, and carry the power to and from the rotor of an AC generator. Brushes B1 and B2 are usually made of carbon. One end of each brush is in contact with rotating slip ring and the other end is connected to the other circuit. Galvanometer is connected to outer circuit. Purpose of galvanometer is to show the flow of current in the external circuit. Furthermore, we will explain the working principle of the AC generator. When the armature rotates between the poles of magnetic field, armature cuts the lines of magnetic field and generates current in the coil of armature. This induced current then flows through the circuits connected to the armature. In fact, it flows through the armature, slip rings, brushes, and through galvanometer, in which we have a response. As you can see, galvanometer needle swings between negative and positive values. This means that alternating current passes through galvanometer. When current is induced in the armature, it's necessary to know the direction of that induced current. So initially, armature coil ABCD is in a vertical position. Armature part AB is up while part CD is down. As you already know, direction of the magnetic field is from north to south pole. Undergo half rotation in clockwise direction, part of armature AB goes down while part CD goes up. According to Fleming's right-hand rule, the thumb indicates the direction of movement of the armature part CD. It is in fact direction of the force, which is upwards. First finger points direction of magnetic field from north to south pole, and second finger shows direction of induced current. In our case, current will flow in direction DCBA of armature and from brush B1 to brush B2 through galvanometer. If we take another half rotation, part of armature AB moves up while part CD moves down. Again, according to Fleming's right-hand rule, the thumb indicates the direction of movement of the armature part CD. It is in fact direction of the force, which is downwards. First finger points direction of magnetic field from north to south pole, and the second finger shows direction of induced current. In our case, current will flow in direction ABCD of armature and from brush B2 to brush B1 through galvanometer. To conclude, induced current changes direction for every half rotation. Next thing we need to see is how induced EMF changes over time. To see this graphically representation of induced EMF, we have to assume that armature needs t seconds to complete full rotation. In time, t equals 0 seconds armature, ABCD is in a vertical position. Part of armature AB is up and part CD is down. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0, therefore induced EMF is 0. For the first quarter rotation, from t equals 0 seconds to t over 4 seconds, part of armature AB moves down and part CD moves up. In this period, induced EMF increases from 0 to maximum value. In t over 4 seconds, armature is in a horizontal position in relation to the magnetic field. In t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value. Therefore, the induced EMF at this position is maximum. During second quarter of rotation, from t over 4 seconds to t over 2 seconds, part of armature AB moves again down and part CD moves up. In this period, induced EMF decreases from its maximum value to 0. In t over 2 seconds, armature again is in vertical position. Part of armature AB is down and part CD is up. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0. Therefore, induced EMF is 0. During the third quarter of rotation, from t over 2 seconds to 3t over 4 seconds, part of armature AB goes up and part CD moves down. In this period, induced EMF increases from 0 to maximum value. But in this period, induced EMF has opposite polarity. In 3t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value, but compared to a position in t over 4 seconds, induced EMF gain its negative value. Finally, during the last quarter of rotation, from 3t over 4 seconds to t seconds, part of armature AB goes up, part CD moves down. In this period, induced EMF decreases from its maximum negative value to 0. In time, t seconds armature is in a vertical position. Again, armature is moving parallel with magnetic field. Rate of change of magnetic flux is 0, therefore induced EMF is 0. From this graphically representation, we saw how induced current changes in time. As you probably already know, the term AC, or alternating current, generally refers to a time-varying waveform or sinusoid, and we saw that sinusoid in this graphical representation. I hope that through this